So we can move ahead with the demonstration session now. So team members Paris and Evan is here. They'll carry on the session.
Yes, ma'am. So, good afternoon, everyone. I hope you enjoyed Harish sir's session. Uh, Before moving ahead, uh, like today we'll be demonstrating airflow and ventilation case study only. So, good afternoon to every CFD enthusiast who are present. My name is Paris Palkar, and I'm working as a research assistant at FOSSEE CFD team in IIT Bombay. And this case study demonstration is a part of the industry readiness workshop. And as Harish sir has very beautifully explained about airflow and ventilation analysis, we are also going to demonstrate and see how we can also um, uh, make our own airflow and ventilation analysis in open form. So again, this is the open forum. I would just like to thank Dr. Kannan, Chandan sir, and Payal ma'am for initiating these such events, and we are really grateful for them because of them we are having these events. So as Harish sir has explained, what is HVAC? So HVAC stands for heating, ventilation, and air conditioning, and air ventilation has a very crucial role in maintaining the air door quality, thermal comfort, and occupant health. And the simulation in the HVAC domains are carried out for buildings, in a means internal domain of vehicles, let's say aircraft or car, and industrial facilities, for example, plume dispersion or something like that. And these simulation helps us optimize the design that we are intending to develop and start the production. So simulations of heat transfer helps us to optimize the design in a better way, rather than just solely depending on the CAD models. So there are general steps that are carried out in a CFD simulation. So in any CFD simulation, this is just not bounded to the R case, but in any simulation, there are four parameters. First is pre-processing, second is solver setup, third is monitoring and solving, and third is post-processing, in which results and interpretation falls. So let us look at them one by one. So the first thing is the geometry creation. So in pre-processing, there are three domains. First is your geometry creation. So geometry you can create using any external CAD modeling software, like FreeCAD or SolidWorks. Even you can use CATIA as well for that. Meshing, same, for meshing you can use block mesh and snappy x mesh. We have had the tutorial for the same in the morning session. And the boundary location, so it is a part of meshing itself. So, and we have to identify which is the boundary patch, and segregation of domains of your CAD model. So these three things are done in your pre-processing. Then we move forward to the solver setup. So solver selection is a very important parameter while setting up any case. Means you have to first identify what you want to simulate. Is it steady state? Is it transient state? Or is it going to implement the density based changes? Or is there something related to compressible flows? So OpenFOAM has a vast category and catalog of solvers. So you have to necessarily choose the ideal solver that is fulfilling your need. And then process, model, and method. So as we solve the Navier-Stokes equation in the solving part, we have to appropriately choose the schemes that are required to solve the particular equation, and same as numerical method setup. And then we go to solving. So in solving, we generally run our simulation, define at for how much time we are going to simulate our simulation. uh, we also, if it is a transient simulation, we have to also carefully monitor the time step, as if we give very high time step value, the simulation will definitely crash. And the current criteria is basically the current number, Current number is used in transient analysis. So we have to specify current number as well in your control dictionary, and it is just current number is just an way of information that is traveling to your particular cell. And then we go to post processing and results interpretation. So in that we analyze flow patterns, we visualize velocity and pressure contours that are occurring. If we are working in HVAC domain, so we also visualize the temperature gradient and is are there any recirculation zones, or if we find like if we are doing an airflow analysis, if we found out there is a dead zone occurring, so we have to optimize the design as well. So we can do that as well just by post processing the data that you have simulated, provided you have done all the three things correctly. If you have fumbled in applying any means appropriate solver, so it is expected that you won't get the results that you are expecting. Okay, so this case study, it is you can go on FOSSEE I'll show you. In the case study, once you go on CFD FOSSEE home, you can go on case study project, and here you can find the completed case studies. And in that, the case study that we are going to demonstrate today is the case number 150. So this is the study of airflow and impact of exhaust, window AC and split AC on air ventilation in the MFST room at IIT Bombay. So it is a real-time simulation that has been carried out by Mr. Akhilesh Pongshe. He was an MTech student under Janani ma'am at IIT Bombay itself. So when they have done some simulations, and we are going to see it. Also, just if anyone who does not have any idea about the how to download the codes, either you can download the abstract only and check what is occurring in this simulation, or you can download the entire case study and reproduce the results yourself. So the title of the presentation is the study of airflow and impact of exhaust on window AC and split AC on air ventilation system in MFST room at IIT Bombay. As I said, the author is Mr. Akhilesh. He was an MTech student at IIT Bombay. And how you can navigate to this study, once you go on cfdfossee.in, in home, go to the case study project, and in that completed case study, and you can find the case study number 150. So you can download either the abstract, or you can download the full codes from the website. And the versions that we are using is OpenFOAM 9. It is the foundation version provided by openfoam.org. So we have there are certain objectives that are being set to demonstrate this case study. So first objective is to understand the significance of air changes per hour to manage the indoor quality. The second objective is to check how adequate ventilation and how to reduce the risk of disease transmission and comfort analysis. Third is this is more about the implementation part. So approximately 25 simulations were carried out by fixing the exhaust position, and the only changing parameter was the horizontal position of the exhaust. And the main interest was to find the air residence at two different heights, that is 1.3 meter and 1.6 meter respectively. So moving further, let us have a discussion on the geometry. So if you are able to see my mouse, this is the indoor door. It will be working as the fluid inlet. The dimensions of the door are 0.8 meter into 1.9 meter. We have attached an AC, air conditioning system here, that is 2 meters above from the wall, and the dimension of the AC are 1 meter in the horizontal length and 0.3 meter in the vertical. And we have also attached an exhaust in the front wall that is 3 meters above from the front wall, and the dimension of the exhaust are 0.5 meter into 0.5 meter. And the modular that in which this geometry has been created is ANSYS space crane. So it is one of the utility in ANSYS for creating your body. So this is the total. This is the way you can visualize the mesh, as it has been made in ANSYS. This is the ANSYS mesh, and this mesh is once we have converted the ANSYS mesh into OpenFOAM mesh. So here you can see there are two exhausts in the ANSYS mesh. One is here and second is here. So parametric study was conducted to check which produces better air resistance residence, single exhaust or dual exhaust. So simulations were carried out for both. This is the AC. You can visualize it here as well, and this is working as the inlet fluid, and you can see it here. And the mesh details are the total cell count is around 1.6 million, and all cells are hexahedral. The skewness is 0.041, which is okay. And what the maximum aspect ratio that the mesh is going is 1.72. So before moving further, we have to make some assumptions. That first thing is the fluid that we are simulating is air, and the air is assumed to be incompressible and ideal gas. So here we are going to implement the K epsilon turbulence model. There are multiple versions of turbulence you can implement, say K omega, K epsilon, laminar, or there are various ones. We can explore that later, but you can implement various turbulence model, and one of which they have implemented is K epsilon. So we have to calculate some numbers to put them into the zero dictionary to carry out our simulation. So we need the values of K, that stands for turbulent kinetic energy. We need turbulent intensity, that stands for I. We need turbulent dissipation rate, that is epsilon, and we have calculated the Reynolds number. Okay, so going first, let us see how Reynolds number is calculated. The Reynolds number is given by density into free stream velocity into your characteristic length upon the viscosity. So that comes out around 13,200. So if you can see, one is the indoor patch that is working as a fluid inlet, and also the AC patch that is also working as the fluid inlet. They have calculated Reynolds number for both, but as the Reynolds number for AC came out to be 12,000 and the Reynolds number for the door came out to be 13,200, so we are going with the higher Reynolds number. After the Reynolds number is calculated, our aim is to calculate the turbulent kinetic energy. But again, for turbulent kinetic energy, we need the turbulent intensity. So the turbulent intensity is given by 0.16 into Reynolds number to the power minus 0.15. That came out to be 0.0487. Once this turbulence intensity is calculated, we put this into the first equation, that is of turbulent kinetic energy. So it is given by, it is K, it is given by 3 by 2 into free stream velocity into your turbulence intensity, and which came out to be 9.735 into 10 to the power minus 5. And once K is done, our next step is to calculate the epsilon. So the epsilon is given by Cu. It is also known as the empirical constant to the power 3 by 4 into your turbulent kinetic energy to the power 1.5 divided by 0.07 into the characteristic length. So here our characteristic length is in horizontal, but if in case there is any internal flow, you can consider it as your diameter as well. So the epsilon value came out to be 2.8 into 10 to the power minus 6. So now let us check boundary condition files in detail. So this is our case structure, if you can see. So this is the zeroth file. So the zeroth file contains all the necessary information regarding the initial and boundary conditions, along with the turbulence property that we are intending to implement. And also the AC inlet flow rate, was taken as 350 cubic cubic feet per minute, and the exhaust flow rate was considered to be 26 meter cube per minute. Once you download this case study now, there are detailed calculation how this particular value was selected, but due to time constraint, I am skipping it. But if you download a whole case study, there is a detailed description how all these values were calculated. Okay. Now coming to the constant folders contains two main parameters. First is transport properties, where we basically tell the open form that which fluid are we using? Are we using air or water, or is there any other fluid? And in the turbulence properties, we specify the turbulence model that we are intending to express, and here in this case we have selected the k epsilon turbulence model. Also, as we have seen in the morning's session, this folder also contains folders like try surface, which contains your STL files, a polymesh folder. Once your mesh is generated, OpenFOAM will create a polymesh folder that will be kept inside your constant folder that contains necessary information regarding the your mesh. And there are also some other parameters, like if you want some dynamic meshing or something, so you can add that as well in the constant folder. And now coming to the system folder. So the system folder consists of the information regarding your simulation. We'll look into it in detail, but just to briefly tell you that what are the internal and external parameters that we are considering. In control dictionary, you can specify what are the things that you are expecting from your simulation, and there is a decompose predict as well. So this decompose predict will help us decompose our case, as we have seen in the morning session while running our simulation on parallel. So to run your simulation on parallel, firstly we have to decompose this particular case into subdomains, and then we have to mesh it, and we can solve a simulation on the decomposed domain. Okay, so before going to the art form and custom solver, let me take you to my terminal. So before going that, let me go to my home directory. As again, I have set an alias to navigate to my OpenFOAM 9 folder. So I'll just type OF9, and it will prompt a message that foundation version has been sourced on which the simulations were carried out. So I'll go to the run folder of OpenFOAM. As I said, the OpenFOAM run folder is located in the OpenFOAM, and you will have your particular name. If you are having OpenFOAM 2412, so it will be defined as your name, and in hyphen in front of the version of OpenFOAM. Here in this case, it is my name hyphen the OpenFOAM foundation version, that is 9. So I will list out all the contents that are there. So here there are some files. We will just go in the necessary ones that we are interested. Okay. So there are two cases. I'll go in T3. Okay. I'll explain you this case in detail. So if you, okay, I have to now. So once you download the whole case study from this domain, once you unzip it, you will get all these necessary files. So let us go one by one and open the readme file here. So it is already open. Okay, so there are some steps that are given. Okay, download the ART form folder and save it. So we will start from the scratch. So here they have basically said that we are going to simulate air residence time in MFST room at IIT Bombay. And here we are going to use simple form, which is a steady state solver. And for that steady state solver, we are going to implement the K epsilon model for flow velocity and simulation. And we are going to use ART form to calculate the air residence time simulation. To successfully run the simulation, you can follow these steps. So first step is to, so basically they are telling us how we can run the whole simulation, it is a very nice way to understand what you are going to do. If you are new to OpenFOAM, or let's say you don't know anything about a particular case study, so at FOSSEE we generally follow rule to whenever we are publishing a case study or research project or lab migration, we put a readme file so that the user who is new to a particular domain can read the readme file and he can start simulating it. So there are some necessary conditions that are used key if you want to compile the solver, how you can do it, and to calculate the air residence, how you can do, and uh, how you can run the simple foam solver. So let us go in the common case first, and in the velocity folder, as they have said, go to your terminal in the run folder and please download the case file called velocity and save it into your run folder in your OpenFOAM. So as I have extracted the whole case study in my run folder, so it won't be an issue. And then by using the command cd, that helps us to go into a particular folder. They are asking us to go in the velocity folder and then type bash, all run there in the terminal. And after completing the successful simulation process, we can visualize the results using Parafoam. So let us go in the velocity folder. So I have already ran this case. I'll just explain what are the boundary conditions and everything that is present. Okay, so we can start from the scratch. So here it is the foam file, and it is the vector field. So you can pay attention to this, that if we are talking about a scalar field or a vector field, so if there is a vector field written, so we are particularly discussing about the vectors. Again, the dimensions are the dimensions that are given to the particular folder. Here as we are discussing with we're dealing with velocity, so the second column stands for meters and the third column stands for time. So the velocity will eventually come out to be meters per second. I'll just convert this to C++. Yes, so the SI unit of this particular field will come out to be meters per second. And we have internal field uniform 000, as internal field are some dumped values that we can place in our simulation. It is similar to the ANSYS initializations, if anyone has used ANSYS. So this is it. And then we will go to the boundary field, where we have defined all of our patches. So first is the inlet. In inlet we have given the fixed value, so the door will work as the inlet, fluid inlet, velocity inlet. And in the negative z direction we are giving a velocity of minus 0.165 meter per second. So in the presentation I told you about that the velocity that we are giving to the solver. So the velocity at the AC inlet flow was taken 350 cubic feet, but here I am writing this, the values are different. So it is because the calculations in the report were done considering cubic feet, and here we are considering meters per second. Okay. Then coming to the outlet, we have specified pressure outlet, zero gradient. The AC is fixed value again, uniform, and we have calculated, we are going to provide the velocity in the x direction as well and in the y direction as well, only in the negative x direction. Once we start visualizing the content, we would be able to see it in a very good, better way. But we will visualize them after some time, because or else the paraview might look very bit clumsy. And then we are going to the wall. So there were multiple walls that were present. Here you can see. So the wall patches have been kept as no slip. Uh, we can open the next pressure folder again. So as I have explained you, this is the pressure, this is the scalar field, these are the dimension of the pressure, and the internal field here is also 0. For inlet we are giving 0 gradient, and at outlet we are confirming it with a fixed value called with 0. Okay, and the wall is also 0 gradient and AC is also 0 gradient. So in OpenFOAM, if you want to write any parameter that are having same boundary type condition, you can write in this way as well. Or if you want, what you can do is, let me comment this out first. What you can do is double comma, we can type like this, and we want our AC, and the AC should be in the in this format. I'll switch to C++. So now, without using or utilizing much space, we have given the type 0 gradient to both wall and AC. That was taking much time. These are some basic, uh, uh, how do I tell you, some basic uh, tricks or tips that you should know. If you are implementing same type of boundary condition, also we can use this same approach for inlet as well. Okay, but now for being, let us keep the way it was. Okay, so the pressure field is okay. Now let us go to the key. As we have calculated the k, so we are just fixing it with the inlet parameter of turbulent intensity kinetic energy inlet. So this is a special type of inlet where you can fix the value, and we can give the value internal field, which is uniform, which is this value. Again for AC we are giving the same field. So as I told in the pressure parameter, we can combine or we can club two patches in a single line using the commands. You can do that for it, do that for these patches as well. So let us say this is outlet, it is set as 0 gradient, and there is wall, and the wall is given the R wall function, and the value is the internal field uniform, that is this value. It is specified previously only. And the AC and inlet values, intensity values, we have calculated it. You can see it here. These are the same values that we have implemented here. We could have given the R wall functions and it would have taken the internal field. But as we have calculated particularly for inlet and EC, so we are giving this turbulent intensity kinetic energy, which helps us to specify what is the intensity of the K. Okay, so this is done. Now let us go to epsilon. Okay. So this is the epsilon folder. It is a scalar parameter. This is the SI unit of it. So after reading this, you can directly jump to the internal field parameter. So we use it generally for initialization of a particular field. Let us say we have to provide some dummy values to the OpenFOAM before actually starting to simulate it. Because if we are giving 0 here and the value is drastically changing at the inlet patch or the particular patch you are interested, there might be some issue in your solution, and either OpenFOAM might crash or it will give you some errors. Okay, so then coming to the boundary field, the type of boundary field that we are the type of condition we are imposing here is turbulent mixing length dissipation rate, and we can specify the mixing length as 0.07. Uh, it is same for AC and inlet, and for outlet we are keeping it as 0 gradient. Again, they have specified AC here, and there is wall, and we generally in until and unless we have the mixing length value, what we generally do is we specify the epsilon wall functions to every patch that we are specifying in your epsilon file value. Okay, so all the files are done, and now we are good to go. If you just open the all run file, so all run file is asking you to clean the foam clean case, then simple foam. Okay, so let me do it. I'll do foam clean case. So it has, so it has, so what we can do now, we can go to, let us say, a particular folder. Let us go to case with common, and let us go to velocity folder, and let's just start running it. So it will run, it will take some time, and in the meantime we can continue our presentation till the solver is running. So ART form, ART form stands for, it is the custom code developed in OpenFOAM that calculates the air residence time. It's air residence time in the particular field. Hence, it is given the name ART, and it solves the scalar transport equation for variable S, and it represents how long the air stays in the particular region. So on the day one, Ivan sir demonstrated you how you can uh, implement the scalar transport form in your particular open form equation. But what is exactly the scalar transport form? So we will understand about that as well. Before doing that, let me open another terminal, open form 9. So the foundation version is sourced. Now I'll go to run directory, clear ls, then I'll go to msd. So we are in this folder, and there is a folder called ART form in the readme file as well. Before simulating our case, our aim is to firstly compile our particular solver and then use the ART form. So they have given how you can compile your particular solver. So by going cd in ART form folder and then type wclean and then use wmake command in your terminal. So wclean command is used whenever you have some pre-existing folders or C++ code remaining in your make file. So if something unnecessary is there, the wclean command cleans it, and if I want to compile the new fresh code, I'll compile it using wmake. So for wmake, there are some definitions. I'll just briefly explain you about it. So the artform.c, the description of this solver is, the application name is artform, and the description of this solver is it solves for the air residence time, and that is ART. So it is calling some header files. What are they? So we'll see. First is create time.h. So if you can see here, it is create time.h. What this file is doing is it is defining our simulation time. Then create mesh.h. So it is loading the computational mesh that we are interested in. Then create fields.h. The create fields is the it reads the s, u, and constant parameters. Keep in mind the s is our air residence time, ART. U is our velocity, and if necessary there are any constant, they are also calculated in this particular file. And then we are implementing a while loop. You can check this. If someone is interested to know more about this, as Ivan sir has said, they can explore the OpenFOAM programmer's guide and check it themselves. And at the end, it is writing all the time steps at the end. And what is the solver's workflow? So what the solver is doing here is it is firstly reading the mesh and the fields that are available. Then we are initializing s and u. So we will firstly run this case called velocity. Then we will compile the solver. As here you can see the solver is running for velocity. We will now compile the solver, and once this velocity folder is ready and ran properly, we will just take the velocity folder from the velocity folder from the velocity case and place it in the ART case. So here in the README file, if you can read, they have specifically mentioned about it, what you have to do. So for running ART air residence case, download the ART folder, save it in your run folder in OpenFOAM, go to the terminal and copy the latest velocity file. So latest velocity file stands for the time being the velocity case has been executed, and paste and replace it with the zero folder in your ART case. Okay, and by using cd command, go in the ART folder and then type bash all run command in your terminal. And after the successful process, you can visualize the results in the parallel. Okay, so in the meantime, what I'll do is I'll list out what is there. Then I'll go in ART form, and first I'll do wclean, and now I'll do wmake. So wclean is firstly I'll list out what is here. So there is a make folder, there is a artform.c, we have just seen it, and this is createfields.h. So it is a header file. So we defined our different values in this header files, and we are just calling it in artform. So we can now compile it. So to compile any solver, all you have to do is just wmake, and it will start compiling. We have some patience, it will compile, and it will yes, it is okay. So the compilation of the solver is done, uh, and if you want to see how we want to, or as we have compiled our solver, but we really want to check if the solver has been compiled or not, so we can use this command. It is called echo command is generally used for calling out some variables, irrespective of anything. The echo command is just used for calling any variable. So we'll do echo home underscore user underscore admin. So here we can see we are having OpenFOAM queries platform, and here we have our solver. And if we want to see art form is particularly present or not, so we can go in the folder called this variable, and we can find if there is art form or not. So let us do that as well. So yes, so we are able to see that art form is there, the source code is successfully compiled, and now we are ready to move towards the ART form simulation as well. Okay, so I'll just come back out of it, I'll list out, and the simulation is running for almost now 1800 time steps. So I'll just terminate it, and I'll go in the directory. So what they have asked us in the readme file is that go in your zero folder, open it, and copy the newest velocity file, copy it and paste it in the ART forms zeroth folder. If there is, so it is asking the velocity file is already existing, do you want to replace it or not? So we'll just hit replace. It is replaced. Now what I'll do is one step backwards, go in ART form, and here again it is doing the same thing. The only difference is here it is calculating the air residence time, and earlier we were solving for pressure and velocity in the velocity case. So I'll just run my all run file, and it has started to solve. So we can wait for some time, or I have a separate folder where I have uh, taken out the results as well. So if you let us see here, and before going to uh, visualization and everything, let us first understand what is scalar transport form. So many of us are from engineering background, and many of us might have been gone through the Reynolds experiment, that helps us to identify the Reynolds number in a particular pipe. So what it does is, what we are doing is, we are just injecting the dye in this pipe to check the nature of fluid. This dye is not impacting the flow parameters. We are just expecting how it will. We are just importing a scalar, and we are trying to see how the internal fluid is going to behave. It is exactly the same. Only thing is, we are going to implement it in the form of air residence in open form. So the only difference here is we are injecting dye in this experiment, and in open form, we are customly writing source codes for it and visualizing it. Okay, so okay, so this case has been the case I have ran here. So we have stopped the simulation at 1800. I have ran it for almost 5000 iterations. So we'll start visualizing it one by one. And in the meantime, I'll zoom out the screen so that it will be better for you to visualize as well. The address, and I'll stop this simulating it as we have already simulated it. Rather than wasting RAM on different solvers, let us just wait. So as you can see here, out of 16, 13.4 GBs of RAM has already been captured. So we'll go one by one and try to visualize the contours that we are expecting. Oh, we have not made any phone.phone file. So here we are just making a phone.phone folder. So the phone.phone folder has been created. So let us go, and we will learn about some basic post-processing methods in Paraview as well. So just hang on for a minute. Okay, so this is the simulation. Uh, we turn on the visible data scale range. So here, if you are able to see, there are two exhausts. One is here and another one is here. The AC is placed 2 meter upwards from the wall. And once I visualize velocity, you will be also able to see the door that is acting as a fluid type inlet. So I'll visualize velocity. So see here, we are able to see the door, the AC, the exhaust, and the dual exhaust. Okay. So now you have extracted this paraview file. but now you want to post process it. And as this is a steady state data, we have not incorporated the transient case or density driven flow, so you will not get any temperature values here. uh, our only aim was to check ki, are single exhaust better or dual exhaust. So for that, what we can do is we can plot some uh, planes. We can take some planes at let us say y normal. You can see here the y is in this case, so we are taking it in y normal, and let us plot it at 1.6. So 1.6 is very downwards. Let's do it 2. Okay, 2 is okay. And in the x direction, it is 2.3. So I'll reduce it to 2 as well. And you can manually change it also if you want to see it like this, or if you want to play with this filter, you can play with it. For the timing, I'll hit apply. So I have extracted this, but we are not able to see anything because of the pressure that is here. Now, once I switch to velocity, you might be able to see this is the AC. But okay, I understand this might be tough. Let me do one thing. I'll reduce the opacity to 0.25, so that you are able to see the velocity here as well, the exhaust portions, and the fluid velocity that is coming from the inlet. Now here, if you are able to see, our plane is just slightly above the door, so we are not able to see the velocity that is coming due to fluid from this direction as well. So we'll just change the direction of the plane to a little bit. Okay, we can position it in the direction of exhaust. So here we can see the fluid velocity is coming from fluid type inlet, and the velocity is also coming from the AC, and it is being captured by the exhaust placed in the back wall. And once we take plane upwards, it will be also captured by this exhaust. Okay, so this is one type of uh, post processing. Let us say you want to change the way we view, or you want to change the color. So what you can do is you can go on slice one, and in that you can edit under coloring section. So there are multiple maps. So I generally prefer rainbow uniform. So now you might be able to see it in a very different way. Let me increase the legend for you, and and we will do it. We will not keep this as velocity. So this is our velocity of AC coming through. This is the velocity of our fluid inlet that is coming, and these are the velocity for the exhaust valve that we have added here and here. So we can, again, if you want, on you have to be very careful while plotting or while switching from one place to another, because what generally happens is you are trying to implement something on form.form file, but it will occur on slice one. Okay, let's say I want to plot glyphs. So if I hit glyph, I want orientation array of view, and I don't want scale array. So I'll turn it off and hit 2.5, and the total number of, let us say, 1000. Okay, so if I hit enter, apply, so here I'll be able to see some recirculation zone. But as this filter is already been applied, let us do one thing. Let us change it into solid color, and here we are seeing the pressure parameter, change it to velocity. Okay, so we will be able to see a small recirculation zone that is occurring here. So it is, and we can see here as well, the velocity is, it is turning a little bit. Also, what you can do is you have plotted the glyph, but you want the glyph on foam.foam. So rather than again selecting foam.foam, again plotting the glyph, what you can do is just hit the glyph, right click it, and go to the change input parameter, and here we can see the select input. It is asking to select me a particular input. So right now, to plot the streamlines, we are using slice, but I want the velocity vectors on the form.form file. I'll hit OK. So now the velocity vectors are throughout the whole domain. Okay, I'll turn this off. They are too much clumsy and I just don't know what is happening. So what I can do is I can again go here and I'll take a plane vertical to this direction. I'll hit apply. So now I won't be able to see anything. Just a minute. As here the again see uh, this the slice, the source of this slice is, if we see, source of this slice is glyphs. So we are plotting slice on the glyph, which is not expected. We want slice on the form.form file. So once I hit OK, so now yes, so it is now working. Okay, so in the negative x direction, I'll click on the slice, I'll turn it off and select the velocity parameter. Again, you won't be able to understand what is happening. So I'll turn on the form.form file and view it in the 3D parameter. And on this slice, I'll try to plot my glyphs. So we are just trying to visualize how the velocity is working in this whole domain and how you can post process your data. Okay. So let us go to orientation array. U is okay. We don't want any scale array. Just a minute. And I want it as 0.25 and 1000. Hit apply. Okay, so these are the pressure contours, but as we are not interested in pressure as of now, you can turn them to velocity and you can visualize as well. -6. So here you are clearly able to see the recirculation zone. If not, let me change the color. I'll just change it to solid color. Okay, so in the 3D case, if you are able to see in the near exhaust, we are also able to see a recirculation zone, and that is really important for us to find out that are there any particular dead zones or recirculation zones that are occurring. So there are basically two recirculation zones, as we can see. First is coming due to the AC's inlet velocity, and the second is coming due to the door that is acting as the fluid inlet's velocity. So there are two recirculation zone in this domain. Okay, let me turn this off. And the form.form file, let us keep it acting. So let us say you want to capture this snapshot of this. So what you can do is, first you want to write something here. So you go on sources and on annotation. Okay, in annotation you can write your 3D text, or you can just basically add your text. So let us say we write as simulation of ventilation at, so the time step here is at 500 seconds. Okay, so I have applied this, but I want it to be bold. So there are some things you can keep this in the center as well. You can do one thing, you can change the font. These are the same fonts that we generally use in our Word file or presentation file. So let us keep it Arial only. Let us change it to 30. So it has increased. We can increase it to 35 as well. And once this is done, we can select the color scheme, that if I want the text in red, it will be displayed in red. But for the time being, let us keep this in black. And if you want to play around the settings, how much parameters do you want? If you want this text to be bold, you can do it. So now this text will be seen in bold. You can bold this particular text. So let us do times. Okay. Uh, in some simulation, the people generally do not require for this XY orientation. So we can turn this off as well by using this filter. So here you can see, if I click it, your XY plane or the 3D plane will be gone. And again, if you want to see the orientation axis, you can hit it. Okay. And again, so here your text is visible, but if you are carrying out a simulation, you have written 5000 seconds here, but how you can prove it? So rather than proving, how you can show it? So again, in annotation, you can go annotate time. Okay. And you have to keep everything as it is. You have to just add, this is basically an advantage. What you can do is just you can add s at the end. So once this is done, you will be able to see the time is 5000 seconds at the end. So let us say if I write seconds, so 5000 seconds will be also seen, but second doesn't feel really good, so we just go with capital S. Okay. And generally we keep it in the bottom. So we are, uh, I mean, the text is written in the upward part, and the font is the time is written in the downward part. I generally follow this way. You can change it as well. So let us say you are using this particular font with let us say 40. The font size is 40, and you want it bold, or you want it italic, or you want the shadow of this text. So there are multiple post processing things that you can do with this. Okay. Also, I would like to show you one filter. So this is, you can use control plus spacebar, and here you can go to plot data. Okay. Plot data, you have to hit enter and apply. Okay. So here it is um, very ill distributed. So what you can do is, here I'll just maximize it. So it will show what it has listed out. So it has listed velocity magnitude, epsilon values, internal k values. So I don't want this. So this will be gone. All I want is the u magnitude. I'll just select this, and I'll close the left axis custom range and bottom axis custom range as well. And I'll just take this. So you can simulate your velocity as well. And if you want to export this, you can plot your velocity as well. If you want to export this into a CSV data, or you want to check these values in your Excel sheet, be careful that you are in this particular window, because what happens is, if you are here, a blue border line will be created if that notates that tells you in which particular window you are working. As we want data from this end, you can select this. A blue line will be created. These are generally beginners level mistakes only, so I am highlighting them, because generally, even when I was learning OpenFOAM, I faced similar mistakes. So what you can do is, if you are on this field, just go here, and there is an option to save data. So it will save it as the file. Let us do demo. Okay. And you're good to go. And here there are choose arrays to write. So I'll select it, and I'll deselect. So all I want is velocity. So I'll just use velocity and hit OK. So it will be saved. I can visualize it later. Okay. First, I'll just tell you how you can do various types of post processing. So again, by clicking this, rather, if you are not comfortable using some hotkeys on keyboard, rather than selecting Control plus spacebar, what you can do is you can go in filters. So there are some tabs. If you are using a particular filter very recently, it will show you that what filters you are working on. And if you want to see all the filters that are available, so just go to the alphabetical part. Just a minute. Uh, yes. On the foam.foam file, just go to the alphabetical part. Here you will be able to see all the types of filters that are existing on the ribbon as well, So you will be seeing the filters that are available on this ribbon. So let us say if you want to extract a contour, or you want to clip this domain, or if you want to take this slice, this will be available. Moreover, some more filters will be also more filters can be also seen. Okay, so let us say you do plot data over time. I'm quite sure keep it will take too much time, and the paraview also will crash due to RAM limitation. So what we can do is we can use the plot data overline, and here, just a minute, I'll turn off the second slice and turn on the first slice. It is bit show plane. I take it bit upwards, so that it is okay. So it has plotted a data particular on the time. I don't want that, and I'll go in plot data overline, change the input, and I want on my slice one. So the plot data on line one will come into play. Here are some settings that you can change. Plot data overline. You can say show line. So if you want to see the line, you can see it. And let us keep the orientation axis also as of now. And let us try to capture some data. Okay. So you can manually move it. Let us say I'm keeping it here and here. So you can see in 2D view, you won't be able to capture it fully. Okay, let us say you have placed your filter like this, but in the 2D view, let us say like this. But once you turn your filter to 3D, again there will be some issues that you are dealing with. Okay, so please take care of that as well before doing. This is what I was saying in 2D view. Let us switch to 3D and just plot a simple basic data overline. Okay. I'll so it is saying that it is showing, but I am unable to see. In that case, what you can do is you can just there is a filter here, render view. So either you can view it in the side, or you can view it in the bottom. So and go in the quartile chart. So if you enter it, and you can basically see all of your parameters that are there in this folder. That is to render view. Spreadsheet view. Okay, I can tell about this as well. So I want to visualize. So what it has done is it has captured all the cell values that are there. Arc length represents the distance of your plot data over line, and it has captured every value. Okay, we can go till the bottom and we can see the arc length, that is almost around 6.32 meters. And as of now it is showing the the velocity, or it there is nothing. So let us change it as well. uh, Change the input source to form file. Okay, again spreadsheet view. And I want plot data overlay. Okay, so as you are able to see the data here, again what you can do is basically you can play around with these filters and test it out for yourself as well. And let us say you have done a particular simulation. Okay, and you want to save it, like you want to save as it is, because once you will open the paraview, you have to do everything from the scratch. So what you can do there as well, you will go in file, and you will go in the save state. Okay, once you save state, there is a paraview state file called .pvsm. It will be saved. So let us do demo.pvsm, and this paraview file is saved. Now whenever you open it, so pvsm file has been saved, and it is asking me how to open. So I'll do it with paraview here. Yeah, so if you are able to see, it will load everything. See, it has opened everything from scratch. All I have done is went into the file and saved the state. Okay, so this was about basic post processing in paraview. Let us now see how we can plot the air residence as well. So I'll do just delete downstream filter. Okay, yes, and I'll go in the velocity folder. We have just copied the velocity folder from ART form, from velocity to this ART form. It has carried out 600 simulation right now. So let us see and try to visualize and see if there is some change. So as you can see, the air residence is occurring. The only thing is we are particularly taking it for some values. Okay, it is still developing. You have to run it for, let's say, almost 2000 seconds or 2000 iterations. Then it will show you some quite good results. So this is the velocity plot, and this is the air residence plot. What you can do is, again, you can take a slice here in the y normal at 1.6 and hit apply, and you will be able to see the air residence as well and how it is behaving in the room. You can check the values from this end, and if you want to change the color scheme, just go in the style editing and select a color map from default. So let us go in rainbow uniform, and from the rainbow uniform, you will be able to see how the time residence is working. Okay, so it is still developing. It is around 350, you may say. Yeah, so it is almost around 350. And by this, you can, by varying the time step data, you can check for particular time step, how much value do you want. Okay, so just let me go to my presentation real quick. We have compiled the solver, we have checked. So this data is from the report, and they have just did the same. We have plotted streamlines, and they have found out recirculation zone near AC and recirculation zone near exhaust. And and we have also simulated the recirculation zone here. So we were able to capture the streamline accurately. And once this time residence plot for exhaust, once your simulation is fully developed, what you can do is, you can go in the again, you can take slices and plot at variable values of height. And in the results and discussion, a small recirculation zone is formed at the top corner of the room besides the AC. Thank you. And this was all from my end. Also, if you can see the case study, this case study was more about machine learning and development of machine learning models for predicting the accurate position of your AC, how accurately you want to place your AC. So this tutorial was more related to that. What you can do is, personally, I haven't checked machine learning for OpenFOAM, but if you are new to it and you want to explore, there are some two files that are given. You can open them individually as well and check for yourself that how they are, what model they are using, what data set they are using, and how they are training data, which model they are implementing, and how much loss is occurring in the machine learning function, and how they are again reincorporating the absolute error. Okay, so this is for 1.3. You can check it out for 1.6 as well. The data set is given here, and in the report you can in deep you can learn about how to implement machine learning models. Also I have as I said, how the Reynolds number came out to be different for so Reynolds number 1 has been considered for calculation, so you can check it out for yourself. They have detailedly explained how they have predicted it. If you can see, this is machine learning data. The red line represents the predicted data, and the blue line predicts the actual data. So it is quite accurate. I won't say quite. I mean, it is nearly around 90% accurate. But if you want to deep dive into machine learning using these solvers, you can do them. Okay. So I'll come on the chat box for now. Let us take some chats as we have some time. Uh, can I show the presentation that I have made in the morning for calculation of 5 plus? If you guys are okay, then we can do that as well. Okay, which case? Okay, Ajit sir. So what you can do is, Mr. Ajit sir, you can go on the CFD FOSSEE home website, and in the home, you will be able to navigate to the case study project. In the case study, here you will see the completed case study. In that, just scroll down and go to the case study number 150. Okay, so this is study of airflow and impact of exhaust on window AC and split AC on air ventilation. There are various machine learning models implemented as well. So here you can see this is an approach of CFD with machine learning. So you can check it out. See, improving air quality in classroom using ART form and machine learning to expedite simulation results. So you can check it for yourself as well, and you can try it out. Okay, I would just like to complete my previous simulation presentation that we were discussing about. Just give me some time. And also just a minute, there is a filter called stream tracer. So Mr. Ivan Fernandez and Mr. John sir from the FOSSEE IIT Bombay team were working on the post processing of this particular case. So they have come up with the particle tracking to test out how a particular parameter of velocity works out. So you can see here I have taken some plots as well. I'll open it with PLC. So here you can see this is the indoor inlet, indoor that is working as inlet. This is working as the AC, and there are two exhaust. So you can see the velocity particle that once the flow develops, how it is going, and it will hit the wall now, and it will change its direction. So you can see it has changed the direction. In this case, we haven't done ray tracing because my system would crash as it is very RAM consuming. But there are various cases as well. Mr. Ivan sir has captured it very nicely. You can see. So here the velocity behaves in different way. So you can try it out for your particular range of interest. You can specify it in ray tracing and check how the air is behaving in your domain. Okay. So let us go to SnappyXmesh PPT. And yeah, I mean, if you want to run your simulation in parallel, so the one command that you are expected to use is lscpu. Just a minute. Yes, so I'll go here, and now I go. Okay, so what I'll do is I'll do now lscpu. Let us do lscpu. So ls is just nothing but just list out your CPU details. So it has clearly mentioned what are threads per core, what are cores per socket, and how much socket do you have. So here, if you want to calculate the physical course, so physical course is given by number of cores per socket into number of socket. Okay, so if you can see, number of cores per socket is 8, and the number of socket that I have, my particular system, is 1. So physical cores that I have are 8 cores, and these are actual cores and processing units in the CPU, and it can execute instructions that we give at a time. Okay, and if I want to find out the total number of cores, so there is different formula, that is number of physical cores that we have calculated in the equation 1 into number of threads per core. So here the number of threads per core is 2. So our case, for my system, it will become 8 into 2, that is 16 cores. If you are uncomfortable with this, it is still okay. What you can do is, you can go in your task manager, performance, and in CPU. Here you can logically check how much logical processors are there, total number of cores are your processors, and how many cores are there. Okay, and see, the socket value is also same, and here is your GPU stat. So I have a dedicated GPU memory of 4 GBs only. Okay, so this information is helpful when you are running your simulation in parallel. Okay, if you are running your simulation in serial, there is but no use of this, but you should know how you can calculate this. So these were commands that we used in the morning session. Okay, so we will just briefly go with Y plus and why it is used. So here you can see there is an airfoil, and here the flow separation is occurring, and you can change the angle of impact for this particular airfoil, and you can calculate the flow separation that is occurring at the trailing edge of the airfoil. So why is Y plus important? Let us understand what is Y plus first. So Y plus is a non-dimensional wall distance used to evaluate the mesh near the wall in turbulent flows. So in turbulent flow, there is too much chaos occurring. So to accurately capture what is exactly happening in this region, we generally model the Y plus. Okay, and this is the importance of it, that it ensures correct boundary layer resolution. Y plus is very helpful in modeling our turbulence as well, and it also helps us to choose the wall treatment approach. So this is let us say this is our wall, and flow is the free stream velocity is coming from this end, you can see. So here the eddies are forming, and there are 3 layers. So one is buffer layer, the second is low region, and this is the outer layer, and this is the edge of the boundary, and ahead it we can see the free stream velocity. So what generally happens is, this is large eddy. LES stands for large eddy simulation. So whenever your cell count is very, 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 very small, we generally tend to keep the Y plus value around 1, where we want to fully resolve the viscous sublayer. Viscous sublayer is this region. We want to accurately capture even a single eddy. Means minute of the minute eddy. When we want to capture the minute of the minute eddy, we aim for the Y plus value of 1. And if we are using any turbulence model like K epsilon or K omega that we saw in the previous heat transfer case study, so we can target any Y plus value of 30 to 300. And even Nikhil sir in today's morning session, he was also talking about the Y plus value, where his Y plus value was around 150. Okay, so you can find various Y plus calculators as well. But if you want to manually calculate your Y plus value, there is a particular way to do that, provided you do some assumptions. First thing, the working fluid that we are considering here is air at 15 degree. The density of air is 1.225 kg per meter cube, and the dynamic viscosity of this fluid is 1.8 into 10 to the power 5 kg per meter second. Here, the main assumption is the free stream velocity, that we are expecting. As the free stream velocity will change, your y plus value will also change. Okay, so just keep in mind, keep to fix your, to calculate y plus, first you have to fix your free stream velocity value. Okay, so as usual, first thing first, we will calculate the Reynolds number as given by density into your free stream velocity into your characteristic length. Here in our case, as we were working on a flow over a cylinder, the diameter of this case was 0.1 meter. So we are using 0.1 here as well. And the dynamic viscosity that comes out to be 34,027, which falls under the category of turbulent flow. And then the coefficient of friction, CF value. So there are two CF values you can calculate. You can calculate one CF value for external aerodynamics, and there are different CF values for internal flows. Let's say you are modeling flow inside a pipe, so the CF value that I'm using here will change. Okay, just find out your CF value and your majority work will be done. Okay, so this is the constant number that we are using, and Reynolds number we are using from equation 1. So 0.058 into Reynolds number to the power minus 0.2. So this came out to be 0.000719. Okay, so we have our CF value as well with us. So we have our Reynolds number, we have our CF value. Now we will be calculating the shear stress. So tau W, it is denoted by tau W. You can calculate it by writing 1 by 2 into your CF value into density into free stream velocity square. So 1 by 2 can be written in form as decimal as 0.5. The CF value can be written as 0.000719 that we have calculated here from 2, CF value from 2. The density that we have assumed here is 1.225 kg per meter cube. And as we have assumed, the velocity that we are going to provide our cylinder will be 5 meter per second. So the square of 5 stands for 25. So we have used 25 here. Okay. So the shear stress value came out to be 0.011 kg per meter second square. After calculating the shear stress, you will go to the velocity shear that is occurring. It is nothing but the under root of the shear stress divided by the density. That came out to be 0.0947 meter per second square. And here we have specified that shear stress we have taken from equation 3. Okay, so we have now our velocity shear. And now first cell thickness y. So in snappy X mesh, if you see, there is a line where you can specify your first cell thickness. Okay, so as we were targeting the y plus value of 1, I have taken it as 1. We are fully resolving the viscous sublayer into dynamic viscosity into this velocity shear and into density. So we are expecting 1 here, y plus value. So our first cell thickness comes out to be near around 0.000155 meter or 155 mm. But in, as you know, in open form, we cannot specify values in terms of mm. So you have to give it in terms of meters. So you can directly write this value in your first cell thickness in Snappy X Mesh. I'll show that as well. Okay, and these are the commands that were used to run your meshing in serial or parallel. The only thing extra we are doing here is decompose power and running the particular solver in parallel. What you can do is you can just replace it. Let us say you want to solve anything. Let us say you want to solve simple form. So you have to just replace it. You have to use decompose power. Only thing changes here is MPR run, and the number of processors will be 10 and the application name will be simple form, and we will be running in parallel. And again, it is up to you. If you want to reconstruct this mesh, you can, but in paraview there is a filter called decomposed case, so you can view it in decomposed situation as well. And there was one thing that I wanted to tell you. Let us say you are making any mesh in ANSYS, and if you want to import it into OpenFOAM, how you can do that? So I have some case with me. I'll try to show you. So this was a folder I was working in my undergraduate days. I was working on a duct simulation. So in that time, while doing my meshing, I made this mesh on ANSYS Fluent, but I wanted it to export it into OpenFOAM. So you have to do nothing. Just go in the system folder. There will be a foam data to Fluent. If you don't know how to find it, as I mentioned, you can go to your tutorials folder. I need to again source my bash RC script. Okay, now we'll go to the examples, and again using the grep command -r, I want to search this fluent data to uh, foam. Let us in. I want to find it in foam underscore. Let us wait for some time. It has jumbled up something. Wait, what we can do is fluent. Okay, so here there is a file called fluent mesh to foam. So you have to do nothing but just go and copy this. It is located in incompressible icofoam folder in the elbow case. You can just copy it, and it is here in our case. What I'm trying to convert is the vent mesh, and here they are trying to convert the elbow mesh. Okay, so I'll do nothing. I'll go here again, and okay, so we are here, and there is the file called fluent data to foam as well. So you have to do nothing. You have to just run fluent mesh to foam, and you have to write the name of the file that you want to convert it into OpenFOAM readable format. So in my case, it is meshvent.msh. The .msh represents the fluent extension. Okay, so just write meshvent.msh. Okay, so see, it has completed, and it is writing it to the constant polymesh folder, and the execution is done. We can check it as well. For that, we need to make a foam.foam file. Okay, and now we can visualize it. Okay, I'll delete this. Okay, so this was the vent. My fluid was coming from this end, and it was getting separated at these channels. So this was only done to check if meshing is working or not. So yes, it is working. This mesh was created in ANSYS, and now we have imported it to OpenFOAM. The only thing we need to take care about of this is while we are developing the mesh in ANSYS, in at that time only you have to specify the name selections. In ANSYS, you have the name selection parameters where you have to specify the names of your particular region. So let us say I named it inlet or outlet. So if that is done, you won't be facing any issue converting your fluent mesh to foam. Okay, and also I have some plots on when I was working on a heat ventilation cooling case. uh, I came out with some files, so you can have a look at this as well. So this is the U magnitude and T temperature, how they are varying with respect to time in your region. Uh, Let us say volumetric 2D. So the chilled air was coming from this end. Using the duct, it went here, and then the aim was to cool this room. So using this post processing techniques, I've done that, and nearly around you can say 2300 seconds, the room started cooling completely. Uh, this is the velocity plot, how the velocity will look like once you render it. This is this is the comparison plot of how your temperature is gradually changing with respect to time. Once the room becomes cool, it will achieve a steady state and a straight line. You can see here. And let me check if I have something. So this was the final video that I demonstrated. This was the 3D view. So the flow was coming from this end, and we captured it in the whole room. And I wanted to see how the flow regimes are working. I took a clip in this direction so that I could see how the cooling is happening in the particular region. This is the top view, uh, top 2D view, where you can simulate or see how it is getting cooled from the top. And this is the temperature value. I have plotted data over time. It is a time consuming filter, but it will work eventually. And once the room is getting cool, the simulation is also reaching the steady state. uh, also uh, Also in Paravel is very good post processing tool. You can select a particular contour and check how it is moving. So in my case, the room was heated at 310 Kelvin, and I wanted to see how the room would look like for the 290 K contour. So you can see as the time progresses, the 290's cold air will start occupying the room, and there was just an outlet that was provided the air to go. And it has started capturing the room. See, uh, as we have had our session on ventilation and flow around the buildings. So in my undergraduate days, I was also working on plume dispersion on some flow analysis. So I have done some flow analysis as well. I have I have these plots, so I'll just show them to you. So you can have an idea how you can post process your data in open form. So this was the building. This is a tutorial case. I haven't developed this from my own. There is a tutorial called flow over buildings. You can find it and you can replicate this as well. So this was the velocity plot. This was the mesh. I have taken a slice uh, along the buildings to check how fine the mesh was. And I have also done some simulation on flow over cylinder. So you can plot your Strawhall number as well. So it was comparison. Let me show you. See, once the flow is being developed, the once the frequency starts, you will be able to see it will start capturing the frequency as well. This was a transient simulation, and it means I did this simulation when I was just learning OpenFOAM. I was not very not very uh, good at it. I was just learning OpenFOAM. So yeah, that's all from my end. I hope you guys have enjoyed it. So yeah, thank you. And yeah, okay. Can you please tell about location and mesh? Okay, very nice point. Okay, so when I was learning open form. So what you can do is you can go in the, let us say, uh, lowers and in the form file. So uh, there was an error due to location in mesh, and I was not able to rectify what was the issue. So what I did was, okay, this is different case. So yes, so there was a particular error I was continuously facing. The location is very ill defined. The entry is very primitive and it is very wrongly defined. So I was not able to figure out what was happening until and unless what happened is, this is the form, and when we specify our location in mesh, na, uh, if it is working, I'll just show you system and snapping. So what I was doing is I was directly giving the values as 0.5, 0.5, and according to the uh, geometry. So I was facing an error. The error was because the point that I was expecting inside my geometry, na, it was coinciding with the nodes that were here. So what a good approach or a steady approach is, what you can do is, again, you can go in filters, search, and you can go to point. So this is a filter called point source. You can hit enter. So your point has been visualized. Okay. And just copy this coordinates and paste them here. Okay. 0.001, 0.001, and it was 0. Hit apply, but you won't be able to see it very nicely. So just change the color of it so that use some dark color so that you will be, and here you can see we are not conflicting with any region inside the mesh. Okay. So sometimes what happens is the point in your mesh will exactly coincide with the domain that you have here. So this is a very good approach. You can randomly move this point as well, but it is a very good approach to, just check by plotting the point source and check that if this point is not conflicting and not causing any issues. Yeah, that was it. And I just want to thank everyone who are present here. You guys have been a very really nice audience. Listen to me, and I hope if you have any questions, you can just directly ask Payal ma'am. She can get back to us.
Everybody is thanking you. It was actually very good session, very detailed one.
Actually, I'm really humbled to get your responses. Thank to Payal ma'am as well. Thank you.